to share some of his exciting work with us. So you can see him in the corner up there, but the screen is obviously shared. And he can see us when we sit on this side. Hopefully he can see. And whenever we have questions, he can hear us through this microphone. So like I'll pass it around and so on. So that's him. I guess, Gary, you're ready? Or you're there to... So, yeah, so... so we are very happy to have Gary Shiu telling us today from Wisconsin about topological data analysis for cosmology and the string landscape. So please go ahead, Gary.
All right. So first off, I would like to thank the organizers for the invitation to speak and for arranging this Skype talk. I really regret that I cannot come in person. There are many talks on the program I saw that I would like to attend, but unfortunately, teaching duties make it difficult to travel at this time of the year. And I really appreciate the opportunity to give this talk remotely. So, as some of you might note, my recent research activities center around the Swampland and string data. However, these two research directions are not completely unrelated. The Swampland program aims to identify the boundary of possibilities for quantum gravity and string theory. So knowing where the boundaries are, we can still make predictions, even though the landscape may be vast. However, it is very likely that even with much progress, we are still left with a huge landscape. The question is, how do we deal with it? Now, an earlier estimate of 10 to the 500 vacua has been superseded by recent studies, and there's no indication that this number will stop growing. So going through this vacua one by one is not feasible. The question is, are there hidden structures in the landscape that may help us understanding the structure of the landscape? Now, in simple cases, when we can visualize the distributions of vacua, we find some interesting patterns. There are vacua that clusters around certain regions of the moduli space. And in some cases, there may even be topologically non-trivial features like voids. And when one looks at the distributions of vacua with additional features, such as enhanced symmetries or vanishing superpotential, one finds even much richer pattern. So how do we recognize this pattern if the dimension of the moduli space is huge, not a two-dimensional space like what is shown here? Interestingly, similar clustering and void features also appear in the large-scale structures of the universe when we look at the distributions of galaxies, density distributions of galaxies and clusters of galaxies. Now, besides the density distributions, we oftentimes are interested in other properties, such as the luminosity and color of the galaxies. And in the case of the CMB, we are interested not only in the temperature fluctuations, but also the polarization information. When we incorporate these features all together, we have a much higher dimensional data space. So how do we recognize this pattern if we have a much higher dimensional space? Now, when the dimension of the data space is huge, we can no longer visualize the distributions of data. We need a more systematic tool. And topological data analysis is a tool in computational topology that could help us diagnose the shape of data in many of these cases. So to turn a discrete set of data points, which is typically the case when we are dealing with data, into a topological space, we need a notion of persistence. The idea of persistence is to consider a nested sequence of topological spaces and track topological features that persist as we vary the continuous parameters that label these spaces. And I will make this more precise as we go along. Now, this is not, this idea of using topological data analysis has been widely used in other fields. For example, in imaging, in the study of neuroscience and drug design. And a point that I like to emphasize is that this systematic approach is oftentimes considered as complementary to machine learning. While a neural network may be effective in classifying patterns, how the machine come up with a decision is oftentimes rather opaque. So you can use TDA in some cases to understand how the classifier works. On the other hand, you can take the output from TDA, things like barcodes and persistent diagrams that I will talk about. You can take them as input to train your neural network. Now, drawing some analogy here, the topology of point cloud describing the chemical compositions of drugs have been used to test the effectiveness of the drugs that is being designed. So one can envision using TDA to test the effectiveness of various early universe theories in reproducing the observed cosmic structure, and perhaps to design a string compactification with certain desired phenomenological properties. Now, due to the huge data volume, going through the entire data set is sometimes not practical and sometimes not even feasible. So in TDA, a selector algorithm is oftentimes used to sample the topology instead of going through the entire data set. And so we can, by way of analyzing the topology of our data, test these algorithms in various physics contexts, not only in the context of imaging, neuroscience, and drug design, but also in cosmology and perhaps in string theory. Now, since one of the themes of this workshop is the energy landscape, let me say a few words about possible applications of TDA to this context, in particular, to the energy landscape of string theory. Now, given a function, usually the function is the potential or the free energy or some physical quantities of interest, we can construct a sublevel set, which is the space, which is the set of points in the field space whose function value is below a certain threshold. Now, Morse theory connects the topology of these sublevel sets with critical points of a potential. So we can use TDA to sample the topology of the sublevel sets so as to find critical points of the energy landscape. In fact, topology change of sublevel sets is often associated with a phase transition, and persistent homology has been shown to recover the expected topology change for some known cases. Now, this naturally suggests that TDA can be used as a tool for the landscape. While questions have been raised regarding the existence of fully explicit and controlled de Sitter vacua in string theory, it is generally believed that there are many Minkowskian and ADS vacua. So in much the same way in the protein folding problem, we can use TDA to sample the topology of the sublevel sets and to find local minima in the energy landscape. And Morse theory tells us that these local minima are related to the appearance of clusters in the sublevel sets. So finding string vacua amounts to tracking the change in the zeroth Betti numbers. So this is an outline of my talk. I will first introduce some basic concepts of topological data analysis, such as persistent homology, barcodes, and persistent diagrams. I will first apply TDA to cosmology to test and constrain primordial non-Gaussianity. Now, since this is a workshop mostly dedicated to string theory and data science, I'll come back to string theory. I'll illustrate how to compute the persistent homology of string vacua data set and use TDA to analyze the structure of the landscape. Now, this talk is based on a series of joint projects with my student, Alex Ko. Our first paper was released last year, and the second installment will hopefully appear shortly. So let me start by introducing some basic concepts of TDA. Now, Many of us are familiar with the notion of topology for continuous manifolds. However, in data analysis, we are not dealing with continuous spaces, but rather discrete set of data points. Nonetheless, we can represent our data in terms of simplexural complexes and perform our topological calculation in the context of simplexural homology. So a simplexural complex is made up of simplices. In lower dimension, the simplices are the vertices, edges, triangles, and tetrahedra that you see in this picture here. And in 3 dimensions, these are all the simplices we have. Of course, we can generalize to higher dimensional cases as well. A simplexural complex is a collection of simplices, is a set of simplices that is closed under taking intersections and faces of simplices in the set. Now, since the data set is represented combinatorically, it is easier to handle computationally. Now, given a simplexural complex, we can compute its topology, we can analyze its topology by computing its homology. Just like for continuous spaces, we can define Betti numbers associated with this simplexural complex. The 0th Betti number counts the number of connected components, whereas the pth Betti number counts the number of independent p loops. And again, because the data set is represented combinatorically, homology calculations amounts to matrix manipulation, which is very easy to handle computationally. But how do we form a simplexural representation of our data in the first place? Now, this procedure is far from unique. It is, of course, very natural to associate each data point with a vertex, with the 0 simplex. However, we have to start making choices when we connect vertices with an edge. So we would like to have a procedure that is stable against different choices of simplexural representation and against perturbation of the data. A procedure that achieves this goal is known as persistent homology. The idea is to consider a nested sequence of topological spaces and track topological features that persist as we vary these continuous parameters. Now, as we vary the continuous parameter, you will see that some topological features appear and some topological features disappear. And we will refer to these instances as the birth and the death, respectively. Now, persistent homology tracks the birth and the death of each distinct topological features. And the intuition that we have is that real topological features persist, while short-lived features are noise. So it's perhaps easier to illustrate this with an example. Here I have a set of points randomly sampled from an annulus. Even without asking a computer, this data set has a clear topological feature with both the 0th and the 1st Betti number being 1. And now we can see how persistent homology can systematically describe the topology of the data set in terms of a sequence of simplexural complex. So first, we have a set of data points. These are our vertices. And we can fatten the points to spheres. And the radius of the spheres will be our filtration parameters. Now, we can connect add 2 vertices by an edge if the spheres overlap. So that's what I do here. And if we will include higher dimensional simplices if all the lower dimensional simplices are included, if all the faces are included. And so we can fill in this triangle. This is our simplexural complex for this value of the filtration parameter. So as you can see, as I vary the filtration parameter, different edges and triangles are included in the simplexural complex. some topological features appears while other topological features disappear. So as I increase further the filtration parameter, we get only one connected component. Moreover, we see that a non-trivial one cycle persists. Now, it is still not a very efficient way to analyze the data. We need a systematic tool to visualize the persistent topology of the data set, and that's why we introduced the notion of barcodes and persistent diagrams. And these visualization tools carry similar information. So what is a barcode? Well, a barcode is a set of lines. Each horizontal lines in the barcode represent an independent cycle contributing to a particular Betti number. So we would have separately the barcodes for Betti number 0, Betti number 1, and Betti number 2, as shown in the slides here. And each horizontal line starts at the birth of the cycle and ends at its death. And so if you were to ask what is the Betti number for a given filtration parameter, all you have to do is to draw a vertical line and count the intersection. Now, persistent diagrams, on the other hand, are scatter plots. Each point represents the moment when the cycle was born and when it dies. So to read off the topology for a given filtration parameter, we can count the number of living cycles, namely the number of cycles that were already born but have not yet died. In other words, the number of points in the upper left quadrant when you draw a line representing the filtration parameter of interest. So a point I would like to make here is that persistent diagrams carries more information than Betti number curves. Now, on the left-hand side, you see that there are two persistent diagrams representing different sequences of births and deaths of a given topological feature. They give rise to the same Betti number as a function of the filtration parameter. Since persistent diagrams tracks the sequence of births and deaths of each distinct topological features and not merely the number of them, we can get more information from the persistent diagrams in contrast to Betti number curves. And we will exploit this to improve the topological data analysis for the CMB. That has been done so far. And you see that that would improve quite significantly the constraints that we can get on things like primordial non-Gaussianity when we look at more refined topological information like persistent diagrams. So let me quickly mention how TDA can be applied to cosmology. We have inflation in mind, but our method can be applied to alternatives as well. As you know, inflation predicts a nearly scale invariant Gaussian spectrum of curvature perturbation, which is in good agreement with data. Now, this curvature perturbation sources anisotropies in the CMB, things that we see from experiments such as WMAP and Planck, etc., as well as inhomogeneities in large-scale structures, where we have a three-dimensional worth of data rather than a two-dimensional worth of data, as in the case of the CMB. The point is that different inflation models predicts different patterns, slightly different patterns of CMB anisotropies. And the taxonomy of inflation that has been done so far is mainly done through two of the observables, namely the spectral index and the tensor to scalar ratio. Now, this is actually the lowest order information we can extract from the CMB anisotropies. The lowest order correlation we can extract from the anisotropies is the power spectrum. In other words, the two-point correlation functions of the curvature perturbations. We can characterize the deviation from scale invariance, which seems to be a very good ansatz, is that we can denote the deviation from exact scale invariance by a spectral index, ns. When ns is 1, the spectrum is perfectly scale invariant. But when ns is different from 1, the spectrum is slightly tilted towards the red when ns is smaller than 1, and blue when NS is bigger than 1. Now, for Gaussian theory, this is all we need because the two-point functions dictates all the higher point correlations. However, the inflationary perturbations are not perfectly Gaussian. The leading non-Gaussianity is the three-point function, or the so-called bispectrum. Now, one can argue, based on scaling and symmetries, that the bispectrum is completely characterized by its overall size, which is oftentimes parameterized by a number that we call FNL, and a two-variable shape function. Shape here means the momentum dependence. As you can see, in contrast to the spectral index, non-Gaussianities are a more powerful discriminator of models, as they could give a functional worth of information and not just a number like a spectral index. Now, the bispectrum for a broad class of models have been computed, including the most vanilla slow roll inflation, as well as inflation models with kinetic terms that are not standard, like dBi inflation or generally K inflation. One finds that the bispectrum for general single field inflation can be parameterized by 5 parameters. And if you were to plot these shape functions, you can easily recognize 2 shapes. One is the so-called local shape, which peaks at the squeeze limit when one of the momenta is 0. And another easily recognizable shape is the equilateral shape, which peaks at the equilateral limit when all the momentum are comparable. Now, this is, in general, a complicated 5-parameter function, and so there could be other shapes as well. And the experts in the audience may ask, what about shapes known as the orthogonal shape? Now, while the orthogonal shape is orthogonal to these 2 shapes that I have shown over here, in the function space, but it looks qualitatively the same as the equilateral shape shown on the right. So this poses a challenge that oftentimes when we use pattern recognition tools in machine learning, some of the subtle but distinct features may not be so easily picked up. Now, more complicated models would give rise to other shapes of non-Gaussianities. For example, if the initial state of inflation is not given by the usual bunch-Davis state, or if the potential is oscillatory, as in axial monodromy inflation, or if there are multiple like fields in the low energy theory, the shape of non-Gaussianities can fall outside the classifications that I mentioned before. Now, like scattering amplitudes in particle physics, these non-Gaussian features can reveal interesting features, it can make interesting statements about the interactions governing the inflaton field. And so you may think of measurements of non-Gaussianity as a way to build a cosmological collider. And in particle physics, as we know, we oftentimes use different strategies to look for different types of particles. So we may also want to use different strategies to look for different shapes of non-Gaussianities. So one way to search for non-Gaussianities is to fit the data with the templates of the bispectrum computed from theory. We can project the data in the sense of distributions on some of the known shapes, like the one that I have shown in the previous slides. Now, there are shapes that are oscillatory, such as the shape that you find in axial monodromy inflation. It has 0 overlap with most templates, and so they are much harder to find. Other than projecting the data into known spectrum, one can also use a mixed topological and geometrical measure known as the Minkowski functionals to constrain non-Gaussianities. So in the case of CMB, the Minkowski functionals include the area fraction below a certain temperature, the length of the boundaries that you identified on the CMB map, as well as the genus of the excursion sets. The excursion set is nothing but the sublevel sets that I mentioned before. Now, combining data fitting with templates together with measures such as the Minkowski functionals, these are the current bounds on non-Gaussianity. So we could apply the TDA techniques that we introduced before to the CMB. And in fact, the method that we outlined can be easily applied to large-scale structured data as well, where we have 3-dimensional worth of data versus 2-dimensional data in the case of the CMB. So here is the temperature maps. The map is color-coded. The hotter temperatures are redder in color. And in the case of the CMB, the filtration parameter is the temperature. So the sublevel sets are the set of points whose temperature is below a certain threshold. So early in the filtration, you see that there are many disjoint connected components and not so many loops. As we increase the filtration parameters, formally disjoint components are now connected, and you see some loops developed. And as we increase the filtration parameter further, we see that we have fewer and fewer connected components, and some of the loops are filled in as the filtration parameter approaches its maximum values. So we first carry out our topological data analysis for local non-Gaussianity because it is the easiest case to study. But we have other shapes of non-Gaussianities in our pipeline. And to make the long story short, we find that persistent diagram can give a more sensitive statistic than other measures that have been considered before, such as the Minkowski functionals or the Betti number curves, simply because persistent diagrams are a more refined set of information about the data. And so persistent homology can strengthen the constraints on non-Gaussianities. Now on the slide, you see that I list the 1 sigma error bar for local non-Gaussianity using persistent diagrams in comparisons to the Betti number curves. And this is a factor of roughly 2 improvement. Now, a 1 sigma error bar of 36 does not look very impressive in comparison to the error bar obtained by fitting the data with templates. If you remember, the error bar for local shapes of non-Gaussianity is about 6. However, bear in mind that the temperature map that we use the temperature maps that we use have a much lower resolution than the temperature maps of that is used by Planck. Now we expect the error bar to drop as the inverse square root of the number of modes. And so the simulations that we use to carry out this TDA was done before WMAP. So now with a lot more modes that are accessible by Planck, we should have redone the simulations to make a fair comparisons with the Planck data. And so just by a simple scaling with the number of modes, it is very conceivable that the error bars that we obtain using topological data analysis will be comparable to that obtained by fitting the data with templates. More importantly, other shapes of non-Gaussianity that are poorly constrained by fitting templates, such as the resonant shape non-Gaussianity of axial monodromy inflation, for such cases, it is conceivable that TDA can give more competitive statistics. All right, so let me now turn to string vacuum. We can apply similar techniques to study the structure of the landscape. And in simple cases, when we can visualize the distributions of vacuum, we find that there are some interesting patterns. For example, if you consider flux vacuum or the rigid Calabi-Yau, there's only a single modulus. So you can actually represent the space of vacuum on a 2-dimensional plane. And here you see that there are clusters and there are non-trivial topological features, the holes where there are no vacuum in between except at the center. Now, it's interesting to explore whether these features that we see in this particular example can be held more generally. Namely, a high degree of topological complexity is associated with a large number of vacuum. or perhaps vacuum with interesting properties. And topological data analysis is precisely a tool to measure the topological complexity of the data set. In high dimensional cases, we can no longer visualize the distributions of vacuum, but we can still compute the persistent homology to uncover some of these topological features. Now, in this talk, I will focus on the landscape of Minkowski vacuum, leaving the interesting question on the energy landscape for future work. So we will start with a simple example where we can visualize the distribution of vacuum as a warm-up. So this is the example that I mentioned before, type 2b flux vacuum on a rigid Calabi-Yau. Since the Calabi-Yau is rigid, we have only the axial dilaton as the modulus. With only a single modulus, we can represent the moduli space on a complex plane, modulo the action of SL2C, which acts on the axial dilaton. So we can compute the persistent diagrams for the distributions of vacuum shown on the right. And from the persistent diagrams, you can see that there are some relatively long-lived topological features. These are the orange dots on the plots. These are the one cycles, and some of the orange dots are lying on the upper part of the plots, and so that they are the long-lived topological features. And they correspond to the appearance of one cycles. And so the presence of these long-lived features means that as we increase the filtration parameter, at some value of the filtration parameter, some one cycle will form. And this one cycles comes with different sizes. The long-lived cycles are the one which has a bigger size because it takes a bigger filtration parameter to fill up the voids. And so these are the voids. These orange dots corresponds to the voids that you see on the picture on the right. On the other hand, the huge degeneracy of vacuum that you find at the center of the voids would show up in the persistent diagrams for the zero Betti numbers. These are the blue dots that lies on the axis. Now, if you have very good eyesight, you can probably see that some of the zero cycles disappear at roughly the same filtration parameter as the one cycle. And this correlated depth can be easily understood. When the filtration parameter becomes big enough to fill up the voids, the points on the vertices on the edge of the voids can now be connected to the center. So at the moment when the one cycle dies, this is also the moment when some of the zeroth cycle die at the same time. But we would like a systematic way to diagnose these correlations. A systematic tool to diagnose these correlations is something known as persistence pairing in TDA. And here we show how these different cycles, the depth of these different dimensional cycles are correlated with each other. So in this example, we see that we can get a lot more information by looking at more refined informations, in this case, persistent pairing, the correlations between different topological features rather than the topological features themselves. So based on this experience, we can up the level of difficulty to consider a higher dimensional moduli space. And in such cases, we can no longer visualize the distributions like what we can do before. Nonetheless, this is precisely the situations where TDA can provide a more useful way to analyze the data. So for that, we will consider a simple case. This is an example of a flux vacuum on a Calabi-Yau orientifold defined on as a hypersurface on a weighted projective space. And so this Calabi-Yau has Hodge number H11 equals to 1, H21 equals to 149. So there's still a lot of moduli. But it also has a large discrete symmetry group. And you can show that the only moduli that is invariant under the discrete symmetries are the complex structure moduli labeled as psi and the axial dilaton. So this is an example which is slightly more complicated than the previous one. Instead of having only one single modulus, you have two. And the other moduli appears in higher order in the superpotentials. So we can consistently set them to 0. And so we can focus on the two-dimensional subspace of the full moduli space without sacrificing any consistencies. Now, if we project, so this is a case where we can no longer visualize the distributions, but if we project the distributions of vacuum onto the psi plane on one of the onto the space of one of the moduli, we see that a lot of vacuum are clusters around the conical points. In doing so, we have lost some information since any projections since we have done a projection, okay? And in our forthcoming paper, we show how TDA can systematically diagnose the structure of the vacuum without having to project onto a data subspace. Now, to identify a cluster, like what was shown in the previous picture, we could introduce the density of vacuum as a filtration parameter. So in such cases, the sublevel set would excise the cluster, giving rise to a clearly identifiable void, as shown on the right-hand side. So finding clusters amounts to finding voids in the sublevel sets with the density of vacuum as the filtration parameter. Now the question is whether this feature survives in the full four-dimensional space, and not only something that you see when you compress the information and project it onto a data subspace. And moreover, are there higher dimensional features that we cannot identify simply by looking at the low-dimensional moduli space? So we can address these questions with persistent homology. We find that there is a long-lived one cycle in the full four-dimensional moduli space using density as the filtration parameter. And at the same time, we find that there are no high-dimensional long-lived features. There are no high-dimensional long-lived cycles when we compute the persistent homology on the distribution of this set of vacuum. And so the clustering that we see in the plots where we project the vacuum onto the psi plane does not occur at a point in the full moduli space. Now, up to this point, what we have studied vacuum that are generic. So an interesting question one could ask is, could imposing additional physical requirements change the topology of the distributions? And we'll illustrate that with a simple example. So we will consider, again, flux vacuum, but this time on a symmetric torus. So symmetric here means that the six-dimensional space is factorizable, and each of the torus has the same modular parameter. So effectively, we have only two moduli in this case, the axial dilaton again, and the complex structure moduli that describe each of the torus. Okay. Now, when we look at the distributions of vacuum, and it was done a long time ago by De Wolf et al., because of flux quantization, some number theoretical techniques were used to find the distributions of vacuum with additional features, such as vanishing superpotentials or vacuum with discrete symmetries. And now, this would be our cuts on the vacuum. And so by cuts, we mean that additional requirements imposed on the set of vacuum. Without the cuts, these are what we call generic vacuum. But we could impose additional cuts, such as imposing the vanishing of the superpotential or the vacuum with discrete symmetries. The former restriction, namely to vacuum with a vanishing superpotential, is particularly motivated because of the Nelson-Seiberg theorem of dynamical supersymmetry breaking. A vanishing superpotential would mean that the R symmetry remains unbroken. So the question is, how could this cuts on the distributions of vacuum change the topology of the distributions? So we find that imposing non-trivial cuts on the distributions can increase the topological complexity. In particular, looking at the distributions of vacuum with a vanishing superpotential in comparisons to vacuum without that additional requirement, we find some non-trivial high-dimensional features that are long-lived. These long-lived features do not appear in the generic set. And so this may point to the fact that topological complexity lead us to vacuum with additional physical interesting features. Now, let me just briefly mention that in general, when we have not one or two moduli, when we have lots of moduli, hundreds of moduli, we cannot realistically include all 10 to the 500 vacuum as vertices of a point cloud. We could nonetheless sample the topology by selecting a set of points as our landmark set. Okay, so many different types of sampling algorithms have been proposed, and they all have the following features. First, you select a set of points as your landmark set. So instead of dealing with 10 to the 500 vacuum, you are dealing with a much smaller set of data points. And so this set of data points can be chosen completely randomly or via the so-called max-min algorithm. And the idea of the max-min algorithm is to select points by induction in order to maximize the distances from the originally chosen set. There are different advantages and disadvantages of doing so. By selecting the points through the max-min algorithm, you are less susceptible to some local bias. So suppose you are selecting points that somehow all fall into a local region of the data space. You may be biased by what happened in the local regions of the space. However, by selecting points that maximize the distance, you also tend to choose points that are the outliers of the distributions. And once you have chosen the landmark set, you could form a simplexual complex known as the witness complex. And so we can perform TDA on this subset of the full set of data to sample the topologies. So I'm coming to an end. So to summarize, it's fair to say that we have learned a great deal about the landscape by learning how to count. And perhaps more can be understood if we also know how to recognize shapes and patterns. So in this talk, I have discussed how TDA can be applied to cosmology to study primordial non-Gaussianity and in studying the distributions of string vacuum. We have shown that persistent homology can strengthen the constraints on local non-Gaussianities, but our method can be applied more generally to other shapes and other observables, and that's next on our to-do list. We have shown that the techniques can be applied to analyze the structure of the landscape. And for simplicity, we have focused our study on the landscape of Minkowski vacuum. And it would be interesting to study the energy landscape using the ideas that I mentioned at the beginning of the talk. Now, even with the restricted set of vacuum, Minkowski vacuum, we have been looking mostly at the distributions of generic vacuum. An interesting next step is to study the topology of string vacuum point clouds with certain desired features, particularly vacuum with interesting particle physics properties. And maybe one can find that there are some topological complexity associated with the distributions of vacuum once we impose these additional features. And so I will stop there. Thank you for your attention.
Yeah, thank you very much, Gary.